Hello, everyone. So last time we were looking at substitution method, how we can use substitution method to solve differential equations using substitution method to solve first order ODEs. We're still in the topic of first order ODEs. And now we want to look at a specific type of equation which can be solved using substitutions. And that is called homogeneous equations. Another application of substitution method. Homogeneous equations. So the general form of a homogeneous equation is an equation of the form, let's say y prime equals capital F of y over x, where capital F is an arbitrary function. To solve this type of equation or this type of ODE, we have to write or use the substitution V equals y over x, and rewrite your equation in terms of v and x. So when we use substitution, we know that we have to change the letters. If originally it's written in terms of y and x, we have to change it to v and x. If you want to go from y to v, then we are not allowed to have y anymore in the new equation. You have to write everything in terms of v and x if you want to change from y to v. So that's what we said last time as well. But for this type of equation, the substitution is v equals y over x. So let's look at this specific example. Example, solve the following equation: x squared y prime equals y squared plus xy with y of 1 equals 1. So there are two different ways to solve this equation. We can write this as a Bernoulli equation, or we can write it as a homogeneous equation. So there are two different approaches to solve this equation, and both, of course, will lead to the same final answer. So answer for this equation can be solved by writing it as a Bernoulli equation or as a homogeneous equation. So approach 1, first approach, as Bernoulli equation, we can write this one as x squared. So this is the equation: x squared y prime equals y squared plus xy. So if I divide everything by x squared, then I'll have y prime minus 1 over x times y equals 1 over x squared y squared. So it's of the form y prime y prime plus p of x times y equals, let's say, q of x y to power n with n equals 2. So we can use the substitution. V equals, if you remember, for solving Bernoulli equation, the proper substitution was V equals y to power 1 minus y to power 1 minus n. So y to power 1 minus 2, which is y to power minus 1. And now I can give this as exercise that you can complete the solution. Complete the solution using this approach. And the second approach, approach number 2, second approach, we can write it as a homogeneous equation. How can we write it as homogeneous equation? Let's write the equation one more time. X squared y prime equals y squared plus xy. Now again, if I divide both sides by x squared, then I'll have y prime equals y squared over x squared plus y over x, which can be written as y over x the whole squared plus y over x. So we can solve this equation by setting v equals y over x. If I set v equals y over x, then I can say that y is equal to v times x. So y prime will be v prime. If I use product rule, v prime x plus v x prime. X prime is 1, so it's going to be plus v. And then I can say that, so y prime is v prime x plus v equals the right-hand side. Right-hand side is v squared plus v. And then v cancels with v, so I can say this is v prime x equals v squared, which I can also write it as dv over dx times x equals v squared. Now, again, like previous examples, if you want to divide by v squared, to take advantage of, having a separable equation. So this is a separable equation in terms of v, of course. We have to divide by v squared. And if you want to divide by v squared, we have to be sure that v is non-zero. Can we say that v is non-zero here? We can say that v is non-zero. Note that y of 1 is 1, which is not 0. So that means y is not the constant function 0. Y is not constant function 0, and v is y over x. So v is not constant function 0 either, because v is y over x. If y is non-zero, not constant function 0, v will be not constant function 0 either. So now that we know v is non-zero, we can divide both sides by v squared. Now, divide both sides by v squared, then we'll get dv over v squared equals x dx. So 1 over x dx. We divided both sides by v squared and also divided both sides by x. So basically we are dividing both sides by v squared times x. Then we get dv over v squared equals dx and multiply both sides by dx. So dx over x. Now integrate both sides. Integrate both sides, then we get integral dv over v squared equals integral 1 over x dx. That means minus 1 over v is equal to ln absolute value x plus c. And therefore v will be equal to minus 1 over ln absolute value x plus c. Okay, to find the constant c, to find c, use the initial condition. What is the initial condition? Initial condition is y of 1 equals 1. And so that means v of 1, v is y over x. So v of 1 will be y of 1 over 1, which is also 1. So v, but what is v of 1? V of 1 will be 1 over minus 1 over ln 1 plus c. And that's minus 1 over c, which is 1. So that gives me c equals minus 1. C equals minus 1. So that means v of x equals minus 1 over ln absolute value x minus 1, which can be written as if I multiply top and bottom by minus 1, then I can write it as 1 over 1 minus ln absolute value x. And we know that v is y over x, so that means y is equal to x times v. So y will be equal to this function here times x. So it's going to be x over 1 minus ln absolute value x. So this is our final answer. Our final answer is x over 1 minus ln absolute value x. This is the solution for our initial value problem. All right, so let's move on to the next section, 1.6, autonomous equations. So autonomous equation, what type of equation is called autonomous in the field of ODE? Definition, any equation or any ODE of the form y prime equals f of y is called autonomous. It's called an autonomous equation. Any equation of the form y prime or dy to dx equals f of y. Okay, now this type of equation is called autonomous because the derivative or rate of change of y does not depend on t, and the rate of change of y is only determined by y itself. So that's why it's called autonomous, because only the value of y controls the equation. There is no need to know the value of t to find the derivative or rate of change. So this is one notation for autonomous equation. Another notation for autonomous equation, which your book uses, instead of using x and y, in this, we said before that instead of x and y, we can of course use t and x. Instead of x as independent variable and y as dependent variable, we can use t as independent variable and x as dependent variable. So another notation which we said usually used in physics. So another notation. Another notation used in physics is x prime equals dx to dt equals f of x. Of course, the concept is still the same. Doesn't matter, use x and t and x or x and y. In any case, an autonomous equation is an equation of this form. So your book uses the second notation. Okay, so the goal here, is to find out about stability of solutions, of an autonomous equation in the sense that if we change the initial condition slightly, do we observe a significant change in the behavior of the solutions as t goes to infinity? So this happens in real life as well, sometimes, something could happen to you, either in a positive way or negative way. Let's say in a very specific moment. Let's say in a very specific moment, you arrive in a specific place and something positive or negative happens to you, which could affect your whole life. As t goes to infinity means even 50 years later, your life is affected by that moment in a positive or in a negative way. Now, that means, if you change the initial condition slightly, you, let's say, arrive 1 second later, 1 second before, maybe, you could observe a significant change in the outcome of your life in, let's say, 50 years later. So this is the meaning of stability. If we change the initial condition a little bit, do we see significant change in the behavior of the function as t goes to infinity, or the behavior of the function as t goes to infinity will be still similar if we change the initial condition a little? Let's say we change the initial time, or for example, childhood. if you behave differently or raise a child differently when he or she is, for example, 1 year old, even if a slight change in the behavior could lead to a different person when he or she, for example, is 50 years old. So in that sense, a slight change in the initial condition could lead to a dramatic change in the behavior of that person in that case as t goes to infinity. Functions are also the same. Some functions, when you change the initial condition a little bit, the final behavior is still similar or changes a little bit. But for some function, if you change the initial condition a little bit, the final behavior would change dramatically. So that's what we want to find out. We want to know about the stability of solutions of an autonomous equation. So now let's consider an autonomous equation of the form y prime equals f of y. Okay, let's consider an autonomous equation of this form. Okay, now a critical point for this equation is a point where f of y is 0. Well, in Math 113, critical points were defined as the points where derivatives are 0. And still we are using same definition. If derivative is 0, that means f of y must be 0. And therefore the roots of f of y would be called critical points for this equation. Question of this form. A critical point for this equation is a y value for which y prime is 0. So here, if I set y prime is 0, then I'll have f of y equals 0. So the roots of f of y are critical points for our ODE. Roots of f of y are the critical points. Now let's consider a specific critical point. Now let y equals, let's say y0 be a critical point for our ODE. For our ODE, then y equals y0 as a constant function will be a solution for our ODE, because if y is equal to y0 or y naught, then dy to dx will be 0, which is same as f of y naught. And this solution is called an equilibrium solution. Equilibrium solution for our ODE. So if y equals y0 as a constant function is a solution for our ODE. We have seen this several times before, because when you have the constant function y equals y0, derivative of this function is 0, and f of y naught is also 0. Why? Because I'm assuming y equals y naught is a critical point for my equation. Critical point for my equation means a root of f of y. So f of y naught is 0, derivative of y is also 0. So that means this is a solution for my ODE. Now this type of solution is called an equilibrium solution. Why is it called equilibrium solution? Because as t goes to infinity, y remains the same. The value of y does not change. It remains the same. So that's why it's called equilibrium. And you can also write this that it is called equilibrium since y of x equals y naught for every x. So the value of y does not change, always remains the same. So that for this reason it's called equilibrium solution. Now we want to know whether this equilibrium solution is stable or unstable. So now we call this solution stable if let's say maybe first I can describe it. If a slight change with a slight change in the initial condition, we still have limit y of x as x goes to infinity equals y0. Mathematically, now let me describe this mathematically. For equilibrium solution, for every equilibrium solution, we have y of x naught equals y naught, and limit y of x as x goes to infinity equals y naught, or a fixed x naught. Now, if you fix an x naught for equilibrium solution, remember, is a constant function y naught. It's always y naught. So y of x naught is y naught, and limit y of x is also y naught. So this is true for every equilibrium solution, whether stable or unstable. Now, if I change the initial condition slightly, now for a stable solution, or stable critical point, we still have limit y of x as x goes to infinity equals y naught with the initial condition conditions of the form y of x naught equals y naught plus epsilon, or y of x naught equals y naught minus epsilon for a small number, small positive number epsilon. See, if the initial condition is y of x naught equals y naught, that means I have a constant function y naught, the solution is constant function y naught, and of course the limit will be y naught, because always the function will be always y naught. Now, if I have an ODE such that in that ODE, instead of considering the initial condition as y of x naught equals y naught, let's say if I change the initial condition to be y of x naught equals y naught plus 0.01, then the solution will be different. The solution will not be constant function y naught anymore. I will have some solution. In that solution, I can still look at the limit of y of x as x goes to infinity. If it is still y naught, and if the similar thing happens for this type of slight change in the initial condition, if instead of y of x naught equals y naught, I have y of x naught equals y naught minus epsilon, and still the limit is y naught as well, then I can say that that point, that a critical point is stable. Okay, so depending on the ODE, on the type of ODE that we have, we can look at the limit y of x as x goes to infinity for a solution of that ODE with the initial condition of the form y of x naught equals y naught plus epsilon, or y of x naught equals y naught minus epsilon. And then look at the limit. If with both these initial conditions, we still have limit y of x equals y naught as x goes to infinity, then that's called stable. So you can probably guess, based on this definition, what type of critical point is called unstable. So based on definition above, a critical point is called unstable if limit y of x as x goes to infinity equals it is not equal to y naught for, or with the initial condition, the initial condition of the form y of x naught equals y naught plus epsilon, or y of x naught equals y naught minus epsilon. So with y of x naught equals y naught, we said limit y of x will be for sure y naught. But if I change y of x naught, the initial condition, instead of y naught, I change it to y naught plus, let's say, 0.001. And then I look at the limit, I will see that the limit is not y naught anymore. Not y naught anymore could be some other fixed number, or could be infinity, could be minus infinity. In those cases, I would call that y naught unstable, because a slight change in the initial condition would change the limit, the ultimate behavior of the function dramatically. Or again, if I change the initial condition to be y naught minus epsilon rather than just y naught, and I look at the limit, I observe that it's not y naught anymore as x goes to infinity. Again, I can say that the critical point is unstable. Let's look at an example. You'll understand better when I give you an example. For example, let's say we can consider y prime equals dy to dx equals, let's say, 2 minus x. 2 minus y, sorry, 2 minus y. So this is an autonomous equation. Autonomous equation because it's of the form y prime equals f of y. Now let's find the critical point first. A critical point for this equation. Let's say critical points for this equation. What should I do for the critical points? I have to set y prime equals 0, which is what you learned in math 113. And then that means 2 minus y equals 0. That gives me y equals 2. I have only one critical point. So that means y equals 2 as a constant function is a solution for y prime equals 2 minus y. Because if y is constant function 2, then y prime is 0, of course. Derivative of constant function is 0, and 2 minus y will be also 0. If y is always 2, 2 minus y will be always 0, and y prime will be equal to 2 minus y. And we said that this type of solution is called equilibrium solution. And according to definition above, this is called an equilibrium solution. So here we have equilibrium solution. Now we want to find out whether this equilibrium solution, or as a critical point, this critical point is stable or unstable. Now let's find out whether this y equals 2 is stable or unstable. So let's consider the same equation, y prime equals 2 minus y, this time with the initial condition with, let's say, y of 0, and let's choose x0 to be 0. To be, instead of 2, let's choose it as 2 plus h. So here x0 is 0 and h is a small positive or negative number. Instead of saying 2 plus epsilon or 2 minus epsilon, I simply call it 2 plus h, and h is a positive or negative number, and I'm choosing my x0 to be 0. And I want to look at, we will look at limit y of x as x goes to infinity, where y is a solution for IVP above, initial value problem above. All right, so let's find a solution for this equation. To find the solution, see, we have y prime equals dy to dx equals 2 minus y, which is a separable equation. And we can say that 2 minus y is not 0, because y of x naught, or y of 0, basically, in this case, is not 2, because it's 2 plus h, where h is a small positive or negative number, so it's not 2. So that means y is not constant function 2, and therefore 2 minus y not equal to 0. So we can divide by 2 minus y, then we get dy over 2 minus y equals dx. Now integrate both sides. Integrate both sides, then we get integral dy integral dy over 2 minus y equals integral dx. So that means minus ln absolute value 2 minus y equals x plus c, which means ln 1 over absolute value 2 minus y equals x plus c. And that means 1 over 2 minus y in absolute value is equal to e to power x plus c, which I can write it as d times e to power x. Here d is e to power c. That means 2 minus y in absolute value is equal to 1 over d times e to power minus x. And that means 2 minus y is equal to plus minus 1 over d times e to the minus x, plus minus 1 over d, I can call it f. So f, I call f, define f as plus minus 1 over d, then I'll have f times e to power minus x, where here f is a positive or negative constant, because d is a positive constant, so plus minus 1 over d is a negative or a positive or negative constant. And then y will be equal to 2 minus f times e to power minus x. And then we can say that to find f, use the initial condition. We know that y of 0 is h. Y of 0 is 2 plus h, if you remember. And then if y of 0 is 2 plus h, y of 0 equals 2 plus h equals 2 minus f. If you replace x with 0 here, y of 0, replace x with 0. So then we'll get 2 minus f. And that gives the value of f to be minus h. So y will be 2 minus h e to power minus x, and that's going to be 2 plus h times e to power minus x. And then, so this is the solution, our solution, the solution for our ODE or IVP, initial value problem. Now we can look at the limit of y as x goes to infinity. That's limit of y of x as x goes to infinity will be equal to limit 2 plus h times e to power minus x as x goes to infinity, which will be 2 plus h times e to power minus infinity. E to power minus infinity is 0. This is 2 plus 0, which is 2. So we showed that even if we slightly change the initial condition from y of 0 equals 2 to y of 0 equals 2 plus h, where h is a positive or negative constant. we still have limit y of x as x goes to infinity equals 2. So that means y equals 2 is a stable critical point by definition. Okay, so when y equals 2 is a critical point, it means that if y of 0 is 2, that means the solution will be the constant function 2. If y of 0 is 2, then the solution must be constant function 2. And if it's constant function 2, then of course limit of it as x goes to infinity is also 2. But now the question is, if I slightly change the initial condition from y of 0 equals 2, let's change it to y of 0 equals 2 plus 0.01, for example, or 2 minus 0.001. Can we still say that the solution still satisfies this condition, still the limit of the solution as x goes to infinity is 2? Well, we just saw that when we slightly change the initial condition, the solution will be completely different now. Instead of y equals 2, if the initial condition is 2 plus h, the solution will not be constant function 2 anymore. It will be 2 plus h times e to the power minus x. So the solution will be completely different. But the limit of the solution as x goes to infinity, we saw that it is still 2. Although the solution is completely different as we change the initial condition even slightly, but still this new solution still satisfies this condition that the limit of it as x goes to infinity is still 2. If this thing happens, then we call the critical point a stable critical point. So if under slight change of initial condition, still the limit of the solution as x goes to infinity is still same number, then we call it stable. Otherwise, we'll call it unstable. Okay, guys.